Finally, checking your work. This is another area for which students are breathtakingly and sometimes hilariously negligent. Here's the thing. If you are 90% correct in your class in physics, most likely you will get the highest possible score. If a scientist or engineer is only 90% correct on their research or their projects, they will be fired and never hired again. If you are working on a multi-billion-dollar project or submitting scientific work for publication on which your career advancement depends, you can't ever be wrong. And there are no answers in the back of the book or on the internet. In the real world, checking your work is correct will often take longer than doing it in the first place. And simply doing it again doesn't cut it because you'll just make the same mistakes. You need to test your answer using alternate methods. An employable scientist and engineer will have a large set of skills concerning solving problems and checking they are right. So let's look at some of them. The first obvious is to check units. So before, I had mentioned that I kept everything in SI units, so my answer should be in SI units. But did the results I have really have consistent units? Well, we can look at that. In my time has units of meters. This has units of meters per second. They are both velocities, and so that's consistent. And meters divided by meters per second is second, which is a unit of time. And I already know then that if that combination has units of time, then that's a unit of time times a velocity, which is a length per time. The times cancel, which give me units of length, and that's consistent with my position. So my relationships do have consistent units. Does the value make sense? Well, 22.2 seconds, 556 meters. The seconds aren't, say, microseconds or years, so that's good. They started 400 meters apart, so 556 meters, which would be 156 meters from the professor. The professor got to run 156 meters before they were caught. That sort of makes sense. They're not too crazy high or low. Do the relationships between physical parameters make sense? How do things scale? Well, for example, here, if the initial position of the professor is larger, time is larger. And that makes sense because the professor started further away. Also, if the difference between the velocities is small, then the time also gets large. That makes sense because it takes longer for the raptor to catch them if they're going nearly the same speed. Also, what this relationship is saying is that if you calculate the relative velocity, the velocity of the raptor minus the velocity of the professor, the time necessary to catch the person is just the time necessary for someone traveling the relative velocity of the objects, the initial separation distance. So I think the relationships do make sense. And then that carries over to this as well. The one thing that's different, of course, if the velocity of the raptor goes up, the position goes up. Does that make sense? Not really, but the velocity of raptor is both in the numerator and the denominator, so that can be more complicated than just sort of a simple scaling. It is true, of course, that if they're further apart, the time increases and so does the position increase. So the relationships between the physical parameters does make some sense. Next, this is a gold mine. Check limiting cases. Check as parameters go to 0 or infinity. If you have angle problems, if the angles go to 0, 90, or 180 degrees, sometimes the motion is really simple, and that will help you identify whether your relationships are correct. Note, here's a good limiting case. In the limit of the two velocities equal to the same, the time goes to infinity, of course. Or, if the velocity of the professor is larger than the velocity of the raptor, then time goes negative. Of course, what that means is that the raptor never catches the professor in either case. Note, if the velocity of the raptor goes to infinity, gets really, really large, then this difference is pretty much just the velocity of the raptor. If the velocity of the raptor is much, much larger than the velocity of the professor, you can sort of ignore that term. Note that these two then cancel, and the position that they're caught is where the professor started. So checking limiting cases is a great way to check that your relationships are right. Also, it goes back to the fact that you can't plug in numbers too early, or you can't check the limiting cases of those parameters. Number 5 I have here is solve the problem a different way. This is great if you can do it. For example, remember This graphical representation I had over here, I know from the graphical representations of kinematics, the area underneath this curve is the total displacement of that object. So that would be the total distance covered by the raptor. And then the area under this curve would be the total distance covered by the professor. Well, I know that the difference in the total displacements of the two objects is in fact their initial separation. When the raptor caught the professor, the raptor covered 400 meters more than the professor did. So just from that graph, I can say that 400 meters is the difference in the displacements, which is the areas of these curves, which is v sub rt minus v sub pt. These are just rectangles, and so the area under the curve is just base times height. And note that gives me the correct relationship instantly. Now, I could have done that before, but I wanted to use this problem to really explore our problem-solving strategies. But we need to pause here for a second, because at the very beginning when I said, ooh, you should do all these different representations, you thought, no, I don't. I want to solve this fast, and that's just a waste of time. However, you would have missed the fastest way to solve this problem. If you'd have gone here, you could solve this problem in maybe half or a third of the time it took than going through all the algebra we did before. Never forget this. Knowing more math, knowing more physics, knowing more tools, doing more visualization, doing more brainstorming will help you solve problems faster. Finally, it can help if you have a really hard problem, is to solve different, simpler problems. You do a lot more of this when the problems get really hard, like research problems that may take weeks or months to be able to solve. A lot of times, you'll take a similar problem where you know the answer, and you do that first to make sure you're doing it right, you have all the right skills, and you have an idea of what's going on. Like, for example, if you write a computer code to solve a problem, you'd never solve your final problem first because you'd have no idea whether your code was working right. You apply your code to a known problem with a known answer to get the bugs worked out. I hope this helps you, and remember, you're practicing on these problems to develop skills that will help you for your career in the long term. I've been a research physicist for over 20 years, and when I tackle a hard problem, I still use this process. In fact, if I'm just doing an introductory physics problem for a homework solution, it's complicated enough, or I haven't seen it before, I still do all of these things. And I don't do all of these things because I'm pedantic. It's because I want to solve physics problems as fast as humanly possible. I love physics, and I still don't want to waste my time doing it. If you want to solve physics problems correctly and quickly, this is how you do it.